Thank you. So I'm going to speak today about some work I did. So I should start by saying I'm currently a postdoc at the University of Edinburgh, and this is my first types. So yeah, thanks. I'm going to mirror what everyone else said and said. It's been a great conference so far. I'm going to actually talk about some work I did at the end of my PhD. So during my PhD, I'd sort of created this type theory, and I wanted to be able to test some things out with it and see what some examples do. So I wanted to write an interpreter or a type checker. I'm kind of going to use the two words interchangeably a bit. And at this time, I was also sort of coming towards the end of the PhD, and I really needed to write a thesis. So I did what any sensible person would do and not write a thesis and over-engineer this completely way too far and then have not very much time to write. So what do I actually want to talk about? I basically want to go over, so I sort of went out into the world of literature and was trying to work out what are the best practices that we can use if we want to be able to sort of run some arbitrary type theory. And there's lots of resources out there. Not all of them apply to everything you want to do, but I'm going to try and summarize sort of my journey with this project in the next, 15 minutes. And yeah, hopefully, I'm guessing for some people in this room, everything I'm going to say will be obvious or may be wrong, but hopefully some of you will find it interesting. So yeah, as an overview, I want to explore really some of the general design principles we have for writing type checkers, evaluators. Yeah, I'm not trying to focus on really the work in particular I did, but just general things that might be able to help anyone who has an urge to try and write some program that's going to sort of check your type theory. So yeah, I sort of split this thing into what this talk is and isn't. So yeah, as I've always said, this is really a report of my experience of trying to do this. And yeah, some of this might be very specific to sort of problems I faced and other people won't face. Some of this will be, I guess, things faced by everyone, but I can't really say. This talk isn't really introducing any novel sort of groundbreaking framework. This is really, I've gone out, there's been lots of resources from various different people, many of who are probably in this room, and sort of tried to pull these things together. And this is sort of the summary that I've come up with. I kind of want to use this chance to try and, I don't know if dispel is the right word, but I thought I'd try and sort of unravel some of the folklore, which I think there's an awful lot of it in this community. And so, yeah, and lastly, this isn't really, I think I've already said this already, but I'm not trying to say anything really specific to the language that I was working with. And in fact, I'm going to go so far as to very purposely try and tell you as little about this language as possible so that we don't get distracted. But having said that, what I am going to tell you is that the language I was working with is weird. So I had no lambda extraction, I had no function types, I had basically none of the things that you would expect in a normal programming language. But I did have some similarities. So I was working with a totally type setting, which with all the sort of complications that comes with. I did, so I was able to sort of do type inference in some locations of things, but we didn't really have a full unification algorithm. So I'm not going to sort of touch on any of the difficulties of type unification in this talk. That will have to wait for once I've figured out how you do that. But we had proved that we had decidable type checking. So we were already starting from a place where we knew this was possible, and we just needed to work out how to implement it. And I'm not going to tell you anything more about this language because otherwise I would have been in a danger of appearing in a directed type theory session. So, and the key question for me was, so we've got this weird language, can we still leverage the existing literature? So I was sort of looking around and a lot of literature started. You sort of open up the page of, here's how you should implement your type checker. And it starts with, right, here's how you represent your lambda abstraction. Here's how you represent your application. And now we do this, this, and this. And look, your beta reduction is solved. And this was not much help to me at all. Or was it? And my answer is yes with an asterisk. So although things did focus on a lot of literature was focusing on how can we implement basically our lambda calculus plus the extra thing you care about. I feel managed to extract sort of some of the core features that actually make these things stick. And so it's probably no surprise to anyone who works in this sort of area that I did manage to sort of pull these ideas together by bidirectional type checking to just sort of cope with the inference part and implement some sort of hacky normalization by evaluation algorithm, which is needed to, so as part of being dependently typed, we need to be able to evaluate terms to even check our type checking. And so once we once we've got these two ideas, I think I'm not sure how so I've come up with this sort of picture of how I view all these things. I think this is at this point a sort of common, or at least one common way of structuring a type checker. And I want to basically spend actually quite a bit of time trying to explain what's going on here. So the core idea is that we're sort of splitting out. So we can view this bit as sort of the bidirectional type checking bit of our type checker, and this bit as sort of the normalization by evaluation bit. I'm not sure how easy it is to see the red laser, but
not at all.
Not at all. Okay. The left bit is the sort of type checking bit. The right bit is the evaluation bit. The keys, the starting point is that instead of trying to bundle everything into one big syntax that has everything, we're going to split our syntax into different related forms. So the point of this first raw syntax form is this is meant to be as close to what is written down in text as possible. So we want, I don't know what I just clicked, but I hope I've not been messed up with that. So the primary purpose of this raw syntax is that we're going to go back and forth between text by passing and printing. So we really want that to actually sort of represent stuff that's going on in our textual representation. And then the idea is that once we've managed to pass something, let's assume for now that that has succeeded, we're going to want to check it. And this core syntax is probably what's closest to what you would find in a paper for describing a type theory. And we want to take our raw syntax that in theory could kind of be anything that at least sort of fit into the syntax. And we want to make sure it all makes sense and get to this core syntax. And the idea of this bidirectional type checking is that we're going to have two different functions to do this. We've got these checking functions where we already know the type that we're trying to aim for, and we're trying to, as the name suggests, check that our raw syntax fits that type. And then the inferring where there'll be certain points in our algorithm where we haven't been given the type, but we're able to infer that what that type should be. And a good example of this inference is when you hit a variable. If that variable's in your context, you're always able to infer what the type of that variable should be. And these two functions, I've sort of drawn them here as separate. This diagram is probably very simplified in that in reality, everything should sort of be pointing everywhere. So these check and infer functions are going to mutually call each other. While I'm checking something, I might need to infer something. While I'm inferring something, I might need to check something. And also, even the sort of where these arrows go to and from isn't necessarily correct. So for example, when we're checking something, well, we actually need a type to check that against. And usually that type will have already been checked. And even in some cases, it might have already been evaluated and be all the way on the right here. So yeah, I'm just going to check how much time I've got.
Why do you need 2 rows?
Why do I need 2 arrows?
No, to go from 20 back to row 2.
Right, so at some point I might want to print something that I've done. And at least the way I have structured this, I'm going to get onto it later that maybe that was a mistake. But at least the way I've structured this is that if I want to print something nicely, it needs to go back to raw syntax. Right, and then the second part on the right is doing our evaluation. And just to make it sort of clear with the dependent typing, at some point in our typing, we will need to check if types are equal. And checking if types are equal, because these types can contain terms in them, we need to be able to check if the terms are equal, and we're doing that by an evaluation. So that sort of just to reinforce this point that all these arrows should really be flying everywhere. And the sort of, to me, this idea of normalization by evaluation means that instead of sort of taking our core syntax and slowly chipping away at it until we can't do any more chipping away, we're instead going to try our best to define what our canonical forms should be, and then we're going to have one big evaluation function that says sort of reduce everything at the same time, get something in this normal form syntax. And then lastly, we have, I think quoting is the standard name. I've seen it by different, few other names, I think, but we need some way to say, well, all our canonical forms should actually be normal syntax as well. So we should be able to interpret it back in. And now I need to remember what happens next. Right, so yeah, my experience of MBE was that it really helped structure the sort of whole algorithm I wanted to do. Even though, so yeah, so what we sort of want to be able to do MBE is we ideally want to know what all these canonical forms should be beforehand. And then we sort of want to interpret everything we had in our core syntax as an operation on this, on these normal forms. But unfortunately, what I started with the language I had was I had this confluent terminating rewrite relation instead. And there was no really clear way to see how this should factor into sort of a normal form. Basically, my definition of a normal form was thing that I couldn't reduce anymore. And I didn't have a sort of better way of doing that. But my takeaway from this was that the normal form syntax I had on the right, it didn't have to be perfect to still get benefits out of this system. There could be things that technically fit into the syntax of my normal form syntax that weren't normal forms. But as long as I sort of did my best, the form of the algorithm still sort of really helped guided what I wanted to do. And the last point, which I'll get onto in a bit, is that it didn't just guide how to structure the algorithm, it actually sort of really helped guide like the formation of an actual efficient algorithm. So my point here isn't that MBE is necessarily more efficient, but I think it encouraged me to be more efficient, if that makes sense. So just to get sort of trying to explain what I mean by MBE. So this is something that I've seen in, it's in loads of, explained a lot differently in lots of different places, but at least my intuition from this implementation perspective is that, I forgot to say earlier, I'm trying to color code all the different syntaxes. I might have missed some. If so, I'm sorry. So we want to evaluate this core term into a normal form term. And to do this, we need some sort of environment, because basically, when we get it, we're going to sort of induct through this term. And when we hit a variable, we need to know what to do. So effectively, this sort of semantic environment is telling us, at least in my case, it was telling us, what do you do when you hit a variable when you're trying to evaluate something? And the simplest way to do that is that you have a pre-evaluated term for each variable that you might encounter. And so in this way, we can sort of view our environment a bit like a substitution. And if we sort of squint enough, we might be able to view what this normalization evaluation is really sort of doing under the hood, at least by the time I've sort of messed around with it enough, is that instead of evaluating this term t, we're really trying to evaluate this sort of this is sort of not a real term because I've mixed together bits of different syntax, but sort of morally, we're trying to evaluate this t substituted by a given sort of pre-evaluated substitution. And then just for an example of this, suppose I actually wanted to evaluate a substitution applied to a term. So we've got this substitution is sort of a list of terms, a list of unevaluated terms, and we've got this environment row. So I've managed to already mess up one of the colors here. So intuitively, at some point, we're going to need to evaluate this term t, like in some point of this algorithm. And so the question is, what environment? We need an environment to evaluate it in. What environment should we evaluate it in? And or at least this is quite, I guess this case is still kind of standard, but one way you could sort of derive this is we could notice that if we go back to this sort of mixed form, we could notice that if we are applying two substitutions, that's the same as actually doing these sort of manglings, and then we actually, so we can put this substitution on the inside of the other one, And then what we see is we're actually substituting this t by evaluating the other substitution, and we get this equation at the bottom. So to evaluate some substitution, we actually evaluate the inner term in the evaluated outer substitution. I don't know if that makes sense, but if it did, wonderful. So something else that I thought, at least one of the lessons to me was that, so I sort of explained this substitution already. I didn't actually have this in the syntax of my language, but I did want to be able to evaluate substitutions. So I had reductions that wanted to substitute stuff. And I knew how to evaluate substitutions, but I didn't have them in the language. So what can I do? Well, I can just add it anyway. So we don't really add much complexity by adding this substitution because we don't have any need to type check it because we're only type checking things in the raw syntax. And we also get this nice property that if we were doing multiple reductions, if you run through what the evaluation does, it doesn't actually have to iterate through the term lots of times. It can actually just squash the whole thing down in one go. And that's sort of what I mean by this guided me to do a more efficient solution. I'm going to go through this one quickly. This is, I think, also quite a common idea, but it turned out to be a great idea to store. I wanted to have variable names everywhere. And so I wanted to be able to remember the variable names everywhere. And storing these things in the binders and context was by far the best way of doing this. I'm appreciative that I'm running out of time, so I'm going to move on from that. It's great that I was after Jan's talk because I also want to reinforce this message that we want to have good error messages. And one of the things that at least I wanted for these error messages is I wanted to remember where they came from. And so one attempt that we might do is that so we had this raw syntax. In this raw syntax, I could try to remember where in my text each thing came from. So for example, here I've got a variable, it has some name. Sorry, I've gone too far. And then I've sort of stored the location in the text that it came from. But then the problem is, if you remember, we had this toRaw function that took our corn syntax back to 3 minutes. And yeah, so we had this thing that sort of took us back to our raw syntax, and then we're not going to know what to put there. So my solution was that we can add a generic type to our raw syntax, and this is sort of, I put an S for this type of spans. And the simple idea is that if we are parsing, we can have this type parameter just be these spans, these ranges, sort of integer ranges. And if we're going from toRaw, this can just be the unit type. And this seems like a kind of neat idea. I don't know if I've seen this before in other places, but I found that very useful while I was structuring this. And then this actually leads on to the first challenge I had, because if you look up here, there was this point here that the reason we needed error handling was that programmers are not perfect. And the corollary of this is that I am not a perfect programmer either. So we had this big diagram of what's meant to be happening. And the idea was that everything on this core syntax and normal form syntax should be sort of well typed. And the problem was that I was implementing all these functions. And so each time I implemented one of these, there was sort of a chance some sort of inconsistency crept in. So maybe we checked some raw syntax and then we got some possibly well-typed core syntax. And then maybe we evaluated it and got some more questionably well-typed normal form syntax. And maybe we quoted that back and everything got even worse. And so this is where I would really like some sort of feedback is, how can we develop good ways to sort of test and check our type checking algorithms as people writing them? I sort of went through some of the sort of kind of solutions I tried to come up with, and everything sort of seems hard to verify. I also, yeah, some other ideas there, which I don't have time to go into. And then the last sort of challenge / propaganda is that I think, so at the end, I tried to sort of extend the type checker I ended up with into sort of a more user-friendly tool, and trying to think about how we can add things like interaction or like nice language server things. And I found this very hard. I found that it was very hard to retroactively add these things on. And so I would really like to see, so I know, of course, all the big proof assistants managed to do these sort of features, and I'd really like to see sort of more sort of theory on how you can structure these big algorithms to take this into account. And yeah, I'll leave the conclusion slide there. Thank you.